In the previous sessions on quality and reliability, we discussed a number of the problems along with the kinds of tools and techniques you are supposed to use to address those problems. So mainly we have concentrated on the tools and techniques related to quality control, related to reliability modeling. What I feel that at this stage a number of the numerical problems, if we discuss, then your understanding will be better. So from this perspective, what I have planned that the next 3 sessions will be explicitly devoting on referring to a few typical numerical problems on both quality and reliability. Now, in this particular session, standardized control charts, which are widely used when sample size is a variable. So, this particular control chart we will be referring to, and a set of numerical problems, typical numerical problems on quality and reliability. Those problems are also I am going to discuss. Now, let us first talk about the standardized control charts when sample size is a variable. If you recollect, when we discussed the control charts for variables as well as for attributes, we have referred to a particular case, and that case is when sample size across the samples may be a variable. There could be many reasons. We have already highlighted those reasons. Now, when the sample size is a variable, obviously the kinds of the control charts you use, which are basically designed for any sample size constant, that may not be applicable. So some special procedures you must bring in to consider the case of variable sample size. Now, under variables category, we have discussed 2 kinds of control charts. One is X bar control charts along with R control chart. So first you use R control chart to control the variability in the process. Once you achieve this condition, that means the variability is under control, then definitely you try to control the process mean for which X bar control chart will be used. As I have already pointed out that both these charts are to be used simultaneously. Now, let us talk about the X bar control chart when the sample size is a variable. Okay, so the reasons could be that the production rate changes from say one particular time period to another, and for each time period you have to draw a sample, and you say that the 10% of the number of say the units you produce, say, okay, will form the sample. So obviously if the number of units or the population size varies, so the sample size also will be varying. So this is just one of the reasons. Now, when sample size is a variable, that means we say that if Ni is the sample size for the sample I, Xi bar and Si is basically the sample standard deviation. So this I have mentioned, that means Xi bar is the sample average and Si is the sample standard deviation for the sample I. Okay. Then you have considered m number of such samples. So when you consider m number of such samples, obviously you compute X double bar, that is the mean of the means or the grand mean, that is sigma I equals to 1 to m Ni Xi. Is it okay? Xi bar. That means this is the sample average for the ith sample, and the corresponding sample size is Ni divided by sigma I equals to 1 to m Ni. That means you sum all the sample sizes. So where m is the number of samples. An estimate of the process standard deviation is given by, that is an unbiased estimate, that is sigma hat, that is root over I equals to 1 to m ni minus 1 si square. This the terms already we have explained, divided by I equals to 1 to m sigma ni minus 1. Is it okay? So this is the expression unbiased estimate of sigma given by sigma hat. So you must have this estimate. Then what you try to do, there are many alternatives you have for designing the control chart. In fact, I have already mentioned that there are 4 alternatives, and one important or preferred alternative is the standardized control chart. So obviously what you need to do, so if you prefer this sort of control chart, that is referred to as the standardized control chart, that means the standardized value for the mean, that is Zi, for the sample I is given by this one. That means Zi is equals to xi bar minus x double bar, okay, divided by sigma hat by root over ni. Is it okay? So that means against each value of xi bar, okay, you need to compute Zi, okay. So and for the Zi, that is this sample the standard deviation, that is sigma hat, already you have computed, divided by root over ni. That means we are assuming normality, and so once you have this value, obviously the center line will be 0, upper control limit as well as the lower control limit will be at 3, that means plus minus 3, that means center line will be 0. In any sort of standardized control chart is used, it is pre-decided, that means center line will be 0, and upper control limit is at plus 3, and lower control limit will be at minus 3. Is it okay? So this rule we follow, assuming that the normality condition holds, okay. Now then we refer to the R control chart. So what you try to do, that means for individual ith sample we compute Ri. How do you compute Ri? That means in the sample you first identify the maximum value, you also identify the minimum value, and the difference between these two is basically the range, that is Ri for the ith sample. Already you have estimated sigma, that is sigma hat. So this the range in terms of sigma, or it is referred to as the relative range. We have already referred to when you derive the expressions for say the control limits of x bar control chart. We have referred to say relative range, that is Ri. Once you have this Ri for small Ri for the ith sample, now you can calculate the standardized value, that is referred to as the Ki Ri minus D2 divided by D3. So that means this is basically the mean of the relative range, and this is basically a function of the sample size, and D3 is the standard deviation of the relative range, okay. We sometimes we refer to another notation, that is W. So the standard deviation of the relative range, that is D3, is also has been proved to be a function of the sample size. So you convert these Ri values into Ki values, and these values are basically the standardized values of the ranges for all the samples. And then obviously the central lines will be 0, and upper control limit, lower control limit will be at plus minus 3. Is it okay? Like you have in the previous case. Is it okay? So this basically is whenever you find that the sample size is a variable, this may be a preferred alternative, and there could be many applications of the standardized control charts, okay. Only thing, one important point you must keep in mind, that the standardized control chart, suppose you deal with the variables data and you use the standardized control chart. Obviously this sort of control chart you may not be able to implement at the shop floor. That means instead of plotting the xi values or say ri values or xi bar values, what you need to do, you need to plot zi values, and then looking at the the patterns, you have to interpret that what could be the possible reasons of say out of control points. Now it may be very difficult for an operator to interpret the value of zi. So that's why what we say that this particular control chart must be handled by the process analysts. Is it okay? Otherwise, it may be very difficult for an operator to identify the possible, the assignable causes against an out of control conditions. Okay, so again we will be referring to such cases when deal with other kinds of the numerical problems. Okay, now let us concentrate on a few typical numerical examples on quality. Is it okay? So and then obviously in subsequent sessions, lecture sessions, I will also be referring to numerical problems on reliability. So first example, what is meant by an overall type 1 error rate? Okay, already we have referred to the type 1 error or the probability of making type 1 error. Is it okay? We have already explained this concept, and the probability, the notation is alpha. Any control chart is used, invariably there will be the probability of making type 1 error. You cannot avoid it. What you can do, that means when you design a control chart, you try to minimize this value, but implicitly it is known that this type 1 error probability exists. There are several rules. If you recollect, we have already discussed 5 specific rules like rule 1, rule 2 and rule 3. Now in a given case, suppose if rules 1, 2 and 3 are used simultaneously, assuming independence, okay, so that means rule 1, if you use it is independent of rule 2. Is it okay? So that sort of assumptions we are making. What is the probability of an overall type 1 error if 3 sigma control limits are used? What we have mentioned that instead of using say one say the rule for out of control condition, is it okay? If you use more number of such rules simultaneously, it is expected that overall type 1 error probability will increase. So so what is that value? Is it okay? Like say if you use rule 1, rule 2 and rule 3, all these 3 rules if you use simultaneously, and if you use 3 sigma control limits, right? Now I need to compute the probability of an overall type 1 error. Now this I'll just explain. Assume that the 3 sigma control limits are used. For rule 1, the probability of a type 1 error is alpha 1, that is 0.0026. Is it okay? That means what is the rule 1? Rule 1 is that what is the probability that a particular sample point will plot outside of the control limits. Is it okay? So if you have plus minus 3 sigma control limits, obviously the probability is 0.0026. On one side it will be 0.0013, on the other side, so the beyond lower control limit, it will be again 0.0013, assuming the central limit theorem holds, and that's why the normality assumption holds. So it is 0.0026. For rule 2, the probability of 2 out of 3 consecutive sample points falling outside the 2 sigma limits. Is it okay? So sometimes the 2 sigma limits are also referred to as the warning limits on a given side of the central line. That means on the same side of the central line. So what is the probability? The probability is the 3 combination 2, 3C2 0.0228, okay, that is the area, on one side, is it okay, the area beyond 2 sigma control limits, that area under the curve, okay, the beyond 2 sigma, on one side it is 0.0028, on the other side again 0.0028. So the two values on one side of the warning limits, the outside the warning limits, that's why it is 0.0228 square into the third point may be anywhere. So this is 0.9772. So this is the probability. Since this can happen on either side, that is the rule, the probability of a type 1 error using rule 2 is obviously twice of this value. That means alpha 2 is 2 into 0.001524, that is 0.003048. Is it okay? So same approach we follow for rule 3. So for rule 3, the probability of 4 out of 5 consecutive points falling beyond the 1 sigma limit on a given side of the center line is again 5 combination 4, 5C4. Now what is the probability that a sample point falls beyond 1 sigma limit? Is it okay, from the center line? So on one side it will be 0.1587, and if you consider the other side it will be 0.3174. So we are considering on one side of the central line, that's why it is 0.1587. Is it okay? And 4 points out of 5 consecutive points, that means 0.1587 to the 4, and the fifth point may be anywhere, that means 0.8413. Is it okay? So this value is this one, and since this can happen on either side of the probability of a type 1 error using rule 3, that means twice of this value, that means 2 times of 0.002668, that means alpha 3 is 0.005336. Assuming independence of the rules, that means as a first approximation, we say that the independence condition holds, the probability of an overall type 1 error is obviously this is 1 minus alpha 1 into 1 minus alpha 2 into 1 minus alpha 3. That means this is the product terms. Is it okay? 1 minus of this one, that means we compute, and ultimately what we find that the overall type 1 error probability is 0.010946. Is it okay? What is this probability 1 minus alpha 1? That means the point will not be falling. Is it okay? What is the probability that this error will not be made? What is the probability that the second type of error will not be made? What is the probability that the third type of error also will not be made? Is it okay? And all three, they are all independent. So obviously it is a product term. And then what is the probability that there will be error? Obviously 1 minus of not making the probability of not having probability of making overall type 1 error. Is it okay? So that is the probability of making an overall type 1 error. So that's why this the product terms are used. Okay, all these individual probabilities are multiplied. So this is the overall probability 0.010946. That means it is very, very high. That means in the 10% of the cases, is it okay, you will be making the type 1 error probability. That means it is basically is a false warning. Okay, you are not going to lose, but what will happen that unnecessarily you will be spending time on identifying the assignable causes, and in many a time you will find that these assignable causes are basically not there. That means the process is not has not gone out of control. Is it okay? So if you have this high probability of making type 1 error, then you become the entire process when we talk about online real-time control of the process. So entire the systems of control may become very unproductive. Is it okay? Now let us talk about the next example. Is it okay? The length of industrial filters, that is say particular product, is a quality of characteristics of interest. Is it okay? 30 samples, each of size 5. That means whenever you design a control chart, you have to specify the value of the sample size. Okay, there are certain rules, there are certain guidelines we have already discussed, and you also must be able to identify, or you should specify, the number of samples. So here 30 samples we have decided, each of size 5, the sample size is 5, are chosen from the process. The data yields an average length of 110 millimeter with the process standard deviation estimated to be 4 mm. That means the process average is known as well as the process standard deviation, that is also known. Okay. Find the warning limits for a control chart for the average length. It is very simple. So usually the warning limits are set at plus minus 2 sigma limits from the center line. Find the 3 sigma control limits. What is the probability of a type 1 error? If the process mean shifts to 112 millimeter, that means as soon as you say that the process mean shifting to another value, it's not 110. That means you are saying that the process has gone out of control. What are the chances of detecting the shift by the third sample drawn after the shift? What we have mentioned, there is a typical control chart, the Shewhart control chart. If the shift magnitude, that means is small, that means 110, and with respect to 110 millimeter, you have constructed the control chart, assuming that the process exists at 110 mm around. Okay. Now suddenly there could be a shift. There could be many reasons. Okay, the sudden shift. If you refer to the control chart patterns, we have referred to the sudden shift, continuous shift, continual shift, and the possible reasons you need to identify. Is it okay? So suppose those reasons do exist, and there is a small shift. Now usually what happens, if you use the traditional Shewhart control chart, there is a least probability, or the probability is very less, that the shift of small magnitude will be detected. Now, so what we are going to calculate, that what is the probability that this shift may be detected by the third sample drawn after the shift. Then the last question is, what is the chance of detecting the shift for the first time on the second sample point drawn after the shift? So this is another case. So how do you get the solution? We follow these steps. The center line on a chart for the average length is 110 millimeters. Already this value is given. The standard deviation of the sample mean is this one. That means the sample standard, the population standard deviation, or the process standard deviation is 4, that is sigma, and the sample size is 5. So obviously sigma x bar will be 4 upon root over 5, that is 1.7888. The warning limits are, this is 110, that is the center line, plus minus 2 sigma. So 2 sigma x bar, that is 2 into 1.7888. That means this, you have these two values. That means warning limit on one side, and this is the warning limit on the other side, 106.4224 and 113.5776. Is it okay? Essentially these are plus minus 2 sigma limits. The 3 sigma control limits are obviously 110, that is process mean, sample mean, and this is basically the process, the sample standard deviation, so 3 sigma x bar. So ultimately the upper control limit, that means at plus 3 sigma from the center line, 115.3664, and the lower control limit, that means on the other side at a distance of 3 sigma from the center line, that is 104.6336. Now what is the probability of a type 1 error? That always you can compute assuming normality, that is 0.0026. Is it okay? That means what you need to do, you need to calculate z values, is it okay, at the lower control limit, and you just compute area under the curve beyond z values, and you note down. So, it will be 0.0013, and similarly you compute the z value at UCL, that is 115.3664. So, you will find the z value will be 3 plus 3, and if you refer to the standard normal distribution, you will find that the corresponding the area under the curve beyond z equals to plus 3 is 0.0013. Is it okay? So, the total area, if you compute, this will be 0.0026. So, the process mean shifts to now. The next problem is that the process mean now had shifted to 112 millimeter. There could be many reasons. So, the standardized normal values at the control limits are, so Z1 it is 115.3664 minus 112, that is the change value of the mean. The standard deviation remains same, that is the assumption. Similarly, at the lower control limit, that is this one, that is 104.6336, you calculate Z2. So, you take the the difference from the change value of the mean, that is 112, and standard deviation remains same. So, that means it is minus 4.118. Then you refer to the standard normal table, and the area above the UCL is this one, that you can read this value from the standard normal table, and area below LCL is almost 0 up to third decimal place, it is 0. And so, area between the control limits is this, that means 1 minus 0.0301 plus 0.0000. So, 0.9699. So, probability of detecting the shift on the first subgroup drawn after the shift, that is this one, 0.0331. The probability of non detecting the shift on the first subgroup and detecting the shift on the second subgroup, assuming independence, is this one. That means, in the first sample, okay, drawn after the shift, there is no detection, that probability is 0.9699, but at the second sample you could detect the shift, and that probability is 0.0301. So, by second sample, what is the probability of detection? That is 0.0292. Similarly, the probability of non detecting the shift on the first and the second subgroup, that is this one, 0.9699. 0.9699, okay, you are unable to detect the shift, but as soon as you reach the third one, okay, your third sample, you are able to detect the shift. The corresponding probability is 0.0301. What we are assuming, that all the sample points, so the samples are independent with one another. So, the corresponding probability is this. Hence, the probability of detecting the shift by the third sample drawn after the shift, that means it is, there are three types of events, that means it can be detected at the first sample point, that is 0.0301. It can be detected by the second sample point, the corresponding probability is this one, and it can be detected by the third sample. So, all possibilities you have to explore. So, if you add these three probabilities, then you have the total probability is 0.0876. The change of detecting the shift for the first time on the second subgroup point drawn after the shift is this one, already we have calculated. That means, by the second sample only, okay, you are detecting by the second sample. So, corresponding probability is 0.0292. Okay. So, now one more problem I am going to discuss, that is example 3 within the next few minutes of time. 25 samples of size 50, that means sample size is 50, are chosen from a plastic injection molding machine producing small containers. Non-conforming containers is produced by a plastic injection molding process. The revised control limits for the P chart are this one. Is it okay? That means, the final control limits are this, upper control limit for the P control chart, that is 0.173, and the lower control limit for the P control chart, that is 0, with the revised center line at 0.067. Construct an OC curve. OC curve, already we have mentioned that with respect to the control chart, you know, we refer to OC curve, and OC curve is considered as one of the performance measures of a control chart. So, the other performance measure is ARL curve, okay, average run length. So, now we need to construct the OC curve as a functions of the process average proportion non-conforming. That is essentially is a plot of beta versus the process parameter. So, how do you calculate this? So, this is the expressions for the beta. That means the value of x is this one. Is it okay? It's a 50 into 0.173 UCL for a given value of 0.10. You need to consider several values of p minus this one. That means x is less than equals to 50 into 0. That means what is the probability that even if there is a shift in the process parameter value, that means suppose the current value is 0.10. What is the probability that the sample point will be plotted within the area defined by the upper control limit and the lower control limit? Is it okay? So, this is the say the beta function for a specific value of p. You compute this one, you follow these steps, and then assuming that that a non-conforming, that the proportion non-conforming is binomial. So, this is the expression. That means the probability you calculate as 0.937. You just follow these steps, and many a time you go for Poisson approximation for the binomial. So, what you try to do, that means you say that I will convert this into from say certain rules you prescribe, okay, later on we will refer to. That means 8.65. That means Poisson distribution is for the discrete random variable. So, but this is not discrete, this is a fraction. So, you say that less than equals to 8, and whereas this is 0. So, that is an integer. So, x less than equals to 0. So, I refer to the cumulative Poisson distribution table, and corresponding value of beta I get, that is 0.925. Is it okay? Many a time as using the cumulative Poisson distribution table is easier than using say the binomial distribution table, and many a time that Poisson approximation to the binomial, okay, the condition is such that is approximation is allowed, or it is well assumed, then you refer to the Poisson cumulative Poisson distribution table to compute such probabilities. So, we can repeat this approach for other values of p to obtain p for each one. So, this way we construct the values. That means these are the possible values of p, and then we compute the values of beta. And once beta is computed, then you say that this is the probability of making type 1 type 2 error. That means this is the probability of non-detection, okay, and you consider on the x axis several possible values of p. So, process proportion non-conforming, which is feasible. So, suppose 10 or 15 such values you consider on one side. So, is a typical OC curve you will get, operating characteristics curves for the P chart. Okay. So, the other examples we'll refer to in the subsequent classes. Okay. So, a plot of beta versus P gives us the OC curve for the P chart. Okay. So, now we need to interpret this control chart. Please go through all these details. Is it okay? So, this way you interpret the OC curve for the P control chart. Is right. So, but the other the examples we will be referring to in the subsequent the lecture sessions.